Okay, let's take a look at a couple of examples of redox reactions, and let's see how we lose electrons and we gain electrons in these two simultaneous reactions. Okay, let's look at this here. We have copper 2 oxide. We have CuO plus hydrogen gas, H2, yielding pure copper metal and water. Okay, when an element is by itself in its natural state, it doesn't have an oxidation number or a charge. So this hydrogen here has a 0 for an oxidation number or charge, and this copper here does as well. Okay, both of those have a 0 charge. They're without charge. When we look at the CuO formula here, the common oxidation number for copper in this case is a +2. Now why is it a +2? When it's a transition metal, and it can often be a +1 as well. Well, it's a +2 here because the oxygen, its common oxidation number is a -2 when in compounds. It can be a -1 if it was in a peroxide. So the copper must be a +2 here so that the net charge on the compound is 0. So the oxygen's carrying a -2, the copper's carrying a +2. Now when we come to the product side, we have water. Okay, the common charge of oxygen is again a -2, and in water, hydrogen, its common charge is a +1, and there's 2 of them, so you see each one is carrying a +1, so the oxidation number would be defined as a +1 for the hydrogen, a -2 for the oxygen, as would it here, and the copper is a +2. Now as we watch the reaction take place, we notice that the copper is going from a +2 to a 0. That is by gaining 2 electrons. And we notice that the hydrogen goes from a 0 to a +1. So it does that by the loss of 1 electron. Remember that electrons are negative, and when we're getting an oxidation number or charge, we commonly take the difference between the number of protons and the number of electrons. So we do the number of protons minus the number of electrons to get that charge. Now, a second reaction that we could look at is this single displacement here between chlorine and potassium iodide. Okay. Now, we notice that when chlorine is in its elemental form, it's all by itself, it's just a molecule, it has no oxidation number, it has no charge. The potassium iodide, what we do is we look at both of these as monoatomic ions, and monoatomic ions take their traditional charge, their ion charge. Group 1 metals, like potassium, carry a +1. Group 17, the halogens, they carry a -1 in ion form. So +1 and -1. The reaction takes place and produces iodine in its elemental, just a molecule here, I2. So again, when it's by itself in just elemental form, it has a 0 charge. And the potassium chloride, the chloride here is an ion, much like the iodide was. Both of these are halogen ions. So it has a -1 charge, and the potassium maintains its +1 charge. So potassium, the ions here, are neither oxidized or reduced. But we notice that our chlorine goes from 0 to the -1 ion. It does that by gaining one electron, and the iodide ion here becomes the iodine molecule there, -1 to 0. How does it do that? By the loss of one electron. Okay? So in oxidation and reduction reactions, we are watching for two processes. We're watching for the gaining of electrons that we classify as a reduction, and the loss of electrons that we classify as the oxidation. Okay? We must have both processes occurring for it to be an oxidation reduction or a redox reaction. Okay? Common examples of redox reactions are the single displacement, like these I've shown you. Combustion are commonly oxidation and reduction reactions. Synthesis and decomposition oftentimes are redox reactions. Okay, so there are a lot of oxidation and reduction reactions that go on around us, and they fall into many of the common categories like synthesis, decomp, single displacement, combustion, and so forth.